Assalamu alaikum warahmatullahi wabarakatuh. This is Dr. Ali El-Moursy, and we are recording the next set of slides for the floating point representation. This is lecture number 26, part 1, and we are actually discussing want to get more insight about and understand more how can the floating point numbers represent the different range of values compared to the integer numbers. First of all, we need in this first part to reflect and think about what kind of ranges and what kind of values that are represented for the integer compared to the floating point. So in the floating point representation does not create something out of nothing. Actually, they still have the limitation of the finite number of real numbers that can be represented, similar to the integer. So if we go back to the integer, we actually can review the following. If I am considering 32-bit register, and this register is used to store numbers in sign to complement representation, that means from the digital logic design, from our knowledge of the sign to complement, this gives me the range of values from minus 2 to the power 31 till positive 2 to the power 31 minus 1. However, those numbers are equally spaced, these integer numbers, so 0, 1, 2, 3 until we reach 2 to the power 31 minus 1. And so the similar thing in the negative. So in both positive and negative, I only represent the integer values. However, the total number of combinations are actually following the rules of DLD. If I have n bits, that means for total I have 2 to the power n combinations. So the number of combinations are 2 to the power 32, split it into two halves, half for negative and half for positive. Okay, starting from minus 2 to the power 31 to 2 to the power 31 minus 1 in the positive. So how it comes right now, the integer representing this value, how can the IEEE standard 754 do something different? The trick here is not with the number of combinations. Since we have still 32 bits used to represent floating point, the single precision, we still have the same limitation of only representing 2 to the power 32 different combinations. However, in the floating point, the ranges of numbers are completely different, as we will see in a minute. So 32 bits IEEE standard with the 32-bit standard do not change the 4 billion representation that we have. However, the 4 billion representations are utilized with equal spaces from the for the range that we have just mentioned, from 2 to the power from minus 2 to the power 31 till positive 2 to the power 31 minus 1. However, the floating point is doing something different. It's actually separating between the numbers differently, as we will see. Before we go and discuss the range of values that can be represented in floating point, we need to emphasize some concepts that we have to mention. So before we discuss the range of values for the floating point, we first want to highlight that some of the combinations, there are set of combinations that are reserved in the floating point. So in the integer there is no reservation of anything, okay? So each number is representing, or each combination representing, a unique number. However, for the single precision, there are some combinations that are reserved. This table is actually giving us a summary about those reserved numbers. So if we ever used the exponent equals to all zeros, okay, this is not a normal number. We have actually two reservations, or two sets for the exponent equals to zeros. If the exponent equals to zeros and also the fractional mantissa equals to zeros, this is actually reserved for the number 0, the absolute 0. So in this case you shouldn't add the 1 in the fractional as we usually did, okay? So this is reserved for the number 0. The second range of values reserved is this second category. It's not only one combination, it's all combinations for the fraction, all combinations for the fraction represented as x here, means don't care, like any value, any combination of fraction with all exponents equals to zeros. This range of values are said to be unnormalized numbers. Okay, so the way of calculation here is different from what we have mentioned before. So if you ever have the exponent equals to zeros, you should not, this does not mean that the exponent is biased. You do not do the biasing or the unbiasing that we did in the last set of slides. This means that you have to take the fraction directly as it is shown here, okay, and do not add the 1. It is actually means this fraction is 0 point fraction, okay? Don't add the 1 and don't make the unbiasing, okay? It automatically means that the exponent is with the value minus 126, okay? So we call this range of values the unnormalized numbers. Unnormalized because there is no 1 added here, and the exponent value 0 we will not unbias it by subtracting minus 127, but it is automatically 126, okay? This is how they set the standard. The second, or the other two sets of special numbers are when all the fraction equals to zeros and the exponent all equals to 1s. This is reserved to the number infinity. So that means if the number that you want to represent is higher than the range that the floating point can give you, so you can indicate that you have an infinity number which is represented or stored in the register or the memory, 32 bits, as all 1s in the exponent, all zeros in the fraction. So this means this is for number infinity. Not only that, if you have an exponent equals to all 1s and you have the fractional mantissa equals to anything, those are not a number. So this is actually the message that you are always maybe get in your programming. So if you are reading a register or memory location, as it is a single precision floating point 32 bits, and these values are being stored inside the register, okay, or the memory location, so this is translated into your computer system as NaN, that this is not a number. So knowing those special cases, we want to exclude those special cases, and we want to see what kind of values that the floating point can represent. So again, here we are reviewing the values with their special cases. All zeros exponent, this is, and with all 1s in the fractional, this is reserved for the value 0. all zeros exponent with any value here, those are unnormalized numbers given by this equation. Any number for the exponent starting from 1, 0, 0, 0, 0 till 0, 1, 1, 1, 1, these are the normal numbers, normalized numbers, with the equation that we have indicated in our last set of slides. This is the equation, the exact equation that we have mentioned in our last set of slides. Okay. So what's else? Hold a second. Okay. Okay. So the all ones for the exponent, the all ones for the exponent is reserved for the infinity if you used the fractional mantissa equals to zeros. Okay, and if your fractional mantissa has any value other than the zeros, this is actually translated as a not a number case in the by your computer system type. Okay, so based on this we know that now the reserved values for the exponents are either all zeros or all ones. Okay, anything in between, this is normalized numbers. Okay, so based on this we can calculate the largest and the smallest number that can be represented using floating point. So for the single precision we have 23 bits for the fractional mantissa, 8 bits for the exponent and 1 bit for the sign. Calculate the range of values for the floating point that can be stored. So in order to calculate the largest integer, I'm expecting to have the largest mantissa, and in the largest mantissa I have 23 bits all equals to ones. Okay, and I can actually don't forget that we have to add 1 to them. So actually this number has the value shown in this equation, and if you want to verify that, we actually have done simple trick in order to do this calculation back in DLD. I know that this is a number that is full of ones. Okay, full of ones until here before the decimal point. So if I add to this number another number that has only 1 here and the zeros otherwise, for all the bits, for all the 23 bits, it is 0. Okay, if I'm adding those two numbers together, this will give me the exact number 1.0. Okay, so if you do this addition, because when adding 1 to 1, 0 and 1 in the carry out, and we will keep this one will be carry out will propagate until it reach to the integer side here. So adding those together equals to the exact 1. So this second number that we have just mentioned here is simply equals to, based on the DLD, this is 2 to the power, so this is 2 to the power minus 1, 2 to the power minus 2 until, so the number of bits here starting from minus 1, minus 2, minus 3 لغاية till a minus 23. So the value for this number is 2 to the power minus 23. Okay, so by simple operation here, so that means this number is simply equals to this, to 1 minus this, 1 minus 2 to the power minus 23. This is actually how this is calculated. This is the calculation shown here. Okay, so don't forget that the numbers is normalized, so that means the largest ever number for the fractional mantissa has 1 plus the larger content. Okay, and the larger content is equals to 1 minus 2 to the power minus 23, so that means it's 2 minus 2 to the power minus 23, which is almost has the value of almost 2, because 2 to the power minus 23 is a very small infinitesimal component. So this is roughly equals to 2. This is for the fractional mantissa. This is the largest fractional mantissa ever. Here this is the largest fractional mantissa. Can we calculate the largest exponent? Can we calculate the largest exponent? Yes, the largest exponent, as our previous slide indicates, the exponent range for the normalized number from 1 0 0 0 till 0 1 1 1 1, because 1 1 1 1 1 reserve it for the infinity and not a number. So this is the largest value for the largest representation for the exponent. Remember that our exponent is biased, so this number is simply 2 to the power it's 254. Okay, if you don't believe me, go back to DLD. So this number has the value 200. This has the value 254. Okay, calculate it using your calculator, but it is biased, so I have to unbias it. Minus 127, so the largest exponent ever is positive 127. Agree? Okay, 254 minus 127 is 127. Okay, and also we can calculate the smallest normalized exponent, the smallest exponent ever, when I have 1 here in the exponent and 0 otherwise, which is mainly the number 1. So 1 minus 127 is 100 minus 126. These are the largest and the smallest. Largest and smallest exponents. Okay, so accordingly the largest integer ever is the largest fraction, okay, multiplied by the largest 2 to the power exponent. Since this is almost 2, that means this is multiplied by 2 to the power the exponent, اللي هو 127. Okay, so accordingly I have the largest number is the positive or negative, almost positive or negative, can be 2 to the power 2 to the power 128. Okay, this is the largest number ever. Remember that for integer, the largest integer ever that we can get is 2 to the power 31. Here I can represent up to 2 to the power 128 because of the floating point representation. Right. Now let's discuss the smallest fraction ever that we can represent. The smallest fraction depends on whether I'm talking about normalized or unnormalized. So let's go back to this table. So for the normalized, I will not reach the minimum, because actually for the normalized I have 1 added to the fraction. But for the unnormalized I have the absolute minimum, because this is actually representing the smallest number. Okay, so if I want to calculate it, I'm better to go for the unnormalized to calculate the fraction. The smallest fraction ever is that exponent will have the value minus 126, as we agree. This is a kind of an agreement for the IEEE standard. Okay, so that means the exponent side will be 2 to the power minus 126. Okay, for the fractional mantissa, it's unbiased, is unnormalized, so there is no 1 added here, so the fraction as it is will be considered. So if I take those two together, I can actually conclude here that the minimum, the smallest unnormalized number is simply given by this equation. So the smallest exponent is 2 to the power minus a 126, as we just indicated in the table. And for the fractional mantissa, it's non-normalized, so I will take it as it is. This is exactly the same number that we have just created 2 slides back. So the smallest ever fraction is when I have 1 in the least significant bit and zeros otherwise, okay, without the normalization, because it's unnormalized number. That means the value for the fraction is 2 to the power minus 23. This is the smallest fraction with the smallest or the largest in negative exponent will give me the smallest infinitesimal fraction ever I can represent in floating point, which is simply equals to plus or minus the fraction 2. I have to add those two powers, so it will be 149 minus 149. This is the smallest fraction ever that can be represented. So from this analysis we can recognize that the representations for floating point are not continuous, because actually the distances between the numbers when I am dealing with the largest exponent ever, if I'm talking about the largest exponents, I have 2 to the power 127, and when I change the value of the fractional mantissa, okay, I'm changing, I have a bigger space or spaces between the numbers for the large numbers, okay. This is at the high end of the representation. But around the zero I can represent infinitesimal numbers, small numbers, with the fractional goes to 102 to the power minus 149, okay. So the distances between the representations is very narrow around the zero, and is getting wider and wider until I reach the high end of the numbers, okay. So this slide is actually showing me, okay, the largest integer, and it has the equivalent largest integer negative, largest integer positive. I have the smallest possible positive and the smallest possible negative, okay, as we just indicated. So to draw those on a chart here, so to cut the long story short, for normalized numbers I have from the exponent 10000 and the fractional reach to all zeros, the value here will be 1 plus zeros. That means 2 to the power minus 126, okay. So this is the starting range or the starting number for the normalized, and by keeps using the different combinations of numbers here, okay, for the fractional mantissa and for the exponent, I can go up to the 0 1 1 1 1 for the exponent and all ones for the mantissa, and this will give me this number that we have just created at the last end of the number here, which is almost close to 2 to the power 128, almost, okay. So very small infinitesimal numbers. So the red bar here shows all the range of values for what? For the normalized numbers. For the unnormalized numbers, that means an exponent should be all zeros, and the mantissa could be either from 1 0 0 0 till all zeros. Since this is are unnormalized numbers, so accordingly we are not adding the 1 here, so we will just take the fractional mantissa as it is. So starting from 2 to the power minus 126, as we agree, multiplied by 2 to the power minus 23 اللي هي 2 to the power minus 149, which is the smallest fraction ever that can be represented. And using different values of the fractional mantissa here, I can go up to all ones here, which gives me actually a number that is very close to the number here, so which is actually very close. So the representations are not continuous. I have some range with different distances for unnormalized, then a little bit of gap, then starting the normalized until I reach the largest number here. So to count the long story short, the smallest fraction ever is 2 to the power 1 minus 149, and the largest number ever is almost, as we mentioned, 2 to the power 128. Okay, this is definitely a huge range of values, from the very small infinitesimal fractions to a very large integer numbers. Still, the number of combinations here of the numbers are 4 billion, but I am not utilizing the 4 billion for either all fractions or integer. I am mixing between them, while the integer numbers, for integers, I have the range for positive and negative from 0 up to 2 to the power positive 31. Very limited range. Okay, very limited range in integer, and this is actually for the single precision floating point representations. Okay, so you have to memorize or you have to memorize well the reserved range. So I encourage you to exactly study this table and know what's the range of how to represent 0, how to represent infinity, how to represent the normalized, and how to represent the unnormalized numbers, and how to represent a not available or not a number range. Okay, so you have to study this very well. Okay, study well. Okay, so this is actually the first part of this chapter, or this set of slides. In the next part number 2, lecture 26, we will actually go and discuss how can I do mathematics, addition and subtraction for floating point numbers. So see you shortly in part 2 of this lecture.